right, let's take a look at some properties of functions. All right, in math, when we're looking at a graph, we always look at that graph from left to right. Right? I mean, we know that. We've dealt with graphs enough before. So as we're looking at a graph, right, and as we're moving from left to right, if the function is increasing, the y values are rising, they're increasing, right? So we can say the y values are rising, right? And that could look like a lot of different things, right? It could be a linear function, it could be increasing like that, right? It could be, lots of different ways that the y values could be rising. If the function is decreasing, then the y values are falling. Okay, again, lots of different possible representations. It could be linear. We could have something like this. Okay, we could have lots of other representations. Last one, okay, we could have a constant piece of a graph. And I should mention, an entire graph doesn't have to be increasing or decreasing or constant, right? We'll look at lots of graphs where just a portion is increasing, a portion is decreasing, maybe a portion of it is constant, right? So the y values stay the same if our function is constant, right? And there's really only one visual representation of that, right? That's if we just have a horizontal line. Okay, that would be our constant representation. All right, so on your notes, okay, it says to look at a few examples out of the book. So I'll just kind of sketch those here. Right, on number 10, we just have a linear function that, I'll do it in a different color. Linear function that looks something like this, right? So we want to describe the intervals over which the function is increasing, decreasing, or constant. Okay, so here, the entire function is decreasing, right? This function starts at negative infinity, goes to positive infinity. So we can just say this function is decreasing from negative infinity to positive infinity. All right. The next one is just a parabola. Right, so I'll go ahead and make a new page here. We've got a parabola with a vertex at 3, 2. So it does something like this and says the vertex is at the point 3, 2. So we want to describe intervals of increasing or decreasing. Okay, and again, we're looking at this from left to right. So the first portion of the graph, okay, moving from left to right, is decreasing, right? That first portion all the way up until 3, 2. And when we're writing these intervals, what we care about is the x value, right? We care about the x value. So we're going to say this function is decreasing from negative infinity all the way up to 3. Right? So negative infinity up to 3. Now, it is actually kind of debated in the math community. I know that sounds stupid, but it's debated whether to include endpoints when we're talking about intervals of increasing or decreasing. I think it makes more sense to say that at that point it's neither increasing nor decreasing. So I'm going to use a parenthesis to denote that 3 isn't included in that. Okay, then we can say that our function is increasing on the rest of the graph. So that would be from 3 to infinity. last graph here that we're going to take a look at looks something like this. All right. And then these coordinate points are at -1, 3, and then this one is at 4, 3, these corners here. Those are the coordinates they give us on that graph. So here, all right, if we're looking at this graph from left to right, I guess we can stick with black. That first portion, okay, on the left, from -infinity up to our x value of -1 is decreasing, right? The y values are going down. I know this one actually kind of looks tricky and trips some people up sometimes because we have that arrow going up. But what we're looking at is this graph from left to right, okay? So that piece is decreasing. So I'm going to say we are decreasing on the interval -infinity up to -1. And remember, we're writing these intervals in terms of our x values. The next piece here in the middle is constant, right? That piece is constant. And those x values looks like from -1 to 4. Then on our final interval, right, from 4 to infinity, our function is again decreasing. So I'm going to put that up here with our little union symbol. So from 4 to infinity. All right. So let's jump up to here. Okay. Maximum and minimum values terminology. All right. So a relative, or we can also call that a local maximum. All right. Another way to say that in layman's terms is just a hill on the graph. All right. A relative or local minimum, we can think about that as a valley. I guess I can sketch in some examples, right? So if we've got some graph that, I don't know, does something like this. Okay, well, an example of a hill could be right here. Okay, that would be an example of a relative max. All right, a relative min could be something like this point. Okay, a valley. And we say they are relative or local because they're not necessarily the highest anywhere on the graph or the lowest anywhere on the graph. They're just the highest or the lowest point in that vicinity. All right. The next one then, an extreme or absolute value, would have to be the greatest value or the smallest value on the entire graph. Okay. So, how do I type that in here? The greatest or the least value on the entire graph. Now, sometimes we won't have an absolute min or max value, right? Because if our function goes off to positive or negative infinity, like in this example that I just drew, right? To the left, we're going to negative infinity. To the right, we're going to positive infinity. There is no absolute min or max here. All right, we'll take a look at some examples that do have absolute mins or maxes. Okay, then a turning point, right, is just where our function. I'll type this out as well. Where a graph changes from increasing to decreasing and increasing to decreasing, or vice versa, right? Where it changes from increasing to decreasing or decreasing to increasing. And in this little green graph up here that I drew, both our local max and local min would be examples of turning points, okay, where the graph changes from increasing to decreasing or decreasing to increasing. Okay, so let's take a look at another example here. All right, on this graph, we want to write down the intervals where the graph is increasing, intervals where it's decreasing, relative maximum points, relative minimum points, and then also turning points. Okay, so I actually want you guys to take a minute and try this one here, and then on your screen, it's going to actually ask you to answer these questions. So take a minute, you can pause the video or just wait for the questions to pop up and give these a try. All right, let's take a look at these here. So intervals where this graph is increasing, all right? Why don't I highlight these? So again, we're looking left to right, right? So it's going to be this piece and this piece. Those would be intervals where the graph is increasing. So let's see, that looks like we go from an x value of 3 to 4, 5, 6. So the first interval where the graph is increasing would be from 3 to 6. All right, so 3 to 6, union that with, what are we at, 6, 7, 8, 8, 2, 9, 10, 11. All right, the graph is decreasing then. Let's use a different color. Let's see, we're decreasing here and here and here, right? And notice those arrows on the left and the right mean that we're going to negative infinity and positive infinity. So that first interval would actually be from negative infinity all the way up to 3. Union that with 6 to 8. And then union that with 11 to positive infinity. All right. The next one is relative maximum points. Okay, relative maximum points are where we see a hill or where the function changes from increasing to decreasing. Right. So I think I see 2 of those. Right. It looks like at x equals 6 and x equals 11. So those coordinate points, let's see, that's 1, 2, 3, 4, 2, 3, 4, 5, 6. Yeah, 6, 6. And that is at 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And relative minimum points. Again, those are like the little valleys, or where we change from decreasing to increasing. So that looks like that happens at 3, negative 2. And at 8, 1. Okay, now it certainly is possible for a graph to not have relative mins or relative maxes, okay? Or it could just have one, right? It could have a relative max or a relative min or none of the above. Then turning points, in this case, every single one of those mins or maxes is a turning point, right? Because the function changes from increasing to decreasing or decreasing to increasing. So we can list all those points here, 6, 6, and 11, 12, and 3, negative 2, and 8, 1. All right. So let's jump on to the back of your notes, okay? Even versus odd. We've actually already kind of looked at this, okay? In an even function, that is where f of negative x is equal to f of x, all right? We tried this already, okay, when we looked at symmetry, okay? An even function is symmetric across the, there we go, y-axis. Okay, an even function is symmetric across the y-axis. Now, we'll take a look at some graphical examples and some examples in terms of functions here in just a second. Then an odd function, right? If I plug negative x into an odd function, I should get the exact opposite of what I started with. Okay, now an odd function is symmetric about the origin. So a few examples of graphs. Again, it says to take a look at numbers 25 through 34 in the book. I'll sketch a couple of them out here. So in terms of a graph, okay, for a function to be even, it just has to be symmetric across the y-axis. For it to be odd, it has to be symmetric across the origin. So first example, let's say we've got a graph that does that. Okay. Is that function, or is that graph, even, odd, or neither? All right, I'm going to let you answer that. So this function ends up being odd, right? If we think about folding this across the origin, okay, it ends up being symmetric. Okay, I know that one's kind of hard to visualize, okay? But in terms of a graph, this is symmetric across the origin. All right, ones that maybe are a little bit easier to visualize are ones that are symmetric across the y-axis, right? So if I sketch, something like that, right? That function would be even, okay? That is symmetric across the y-axis. All right. What about something like this? Let's do that. All right, a nice straight line, just kind of like that first example. So is this one even, odd, or neither? This one actually ends up being neither, right? Here, this graph is not symmetric across the y-axis, and it's not symmetric across the origin either, okay? There's no way to, I know, this is hard to visualize, but folding something across the origin, right? This one is neither. All right, let's do one more. How about something like this? Okay, this is looks like a cubic graph, right? So is this symmetric across the y-axis, across the origin, or neither? On this one ends up being symmetric through the origin. Okay, when we're looking for symmetry through the origin, what we can kind of think about is, well, if I reflect half of this across both the x and the y-axis, right? Does it match up? Okay, if I reflect these pieces across the x and the y-axis, they will match up, meaning this one is odd. Okay, so in terms of a graph, even means symmetric across the y-axis, odd means symmetric across the origin. All right, so given an equation, what does this mean? Okay, well, given an equation, we want to plug negative x in. If our function is even, we'll get exactly what we started with. If our function is odd, we'll get the exact opposite of what we started with, okay? So let's take a look at this first example, right? For any of these, if I'm testing for even or odd, right, either one, that means plug in negative x, right? So we can negative x for x, okay? In other words, we're evaluating f of negative x. So if I plug negative x in here, I'm going to have negative x squared minus 9. Okay, well, negative x squared would just be x squared minus 9. Plugging in negative x, I get the exact same thing as what I started with, right? So here we can say that f of negative x is equal to f of x, right? That means that this function is even, all right? Take a second and give b a try here. All right, so on this one, if I plug negative x in, right, so g of negative x will be negative x cubed. Well, negative x to the third power is still negative x, right? So this would still be negative x cubed, but I've got a double negative, so this just ends up being positive x cubed, all right? Well, I started with negative x cubed, I got positive x cubed. This function is the exact opposite of what we started with. That means that this is an example of an odd function. Okay, now something that usually creeps up as a question, okay, or maybe a misunderstanding. If I have multiple terms, every single term would have to have the opposite sign for it to be odd, okay? For even, every single term would have to have the same sign, okay? But for it to be an odd function, when I plug in negative x, every single term in that function would have to have the opposite sign of what we started with, all right? One last idea here. We're going to take a look at the difference quotient. Okay, this is for those of you that are planning on going on to calculus next year. This is a very important idea. Okay, we're not going to get into the calculus of it, but we have to make sure that we understand the algebra this year. All right. So the difference quotient is f of x plus h minus f of x over h. Well, if we're given some function, say negative 7x, I have to first evaluate f of x plus h, okay? Well, what that means is I want to plug x plus h in everywhere I see an x. So this would become negative 7 times x plus h, which we can simplify that, right? And that would become negative 7x minus 7h. So now we're going to plug that into our difference quotient. Okay, so what's going to happen, I'll do this in a different color. All right, if I'm using this f of x plus h minus f of x all over h. Okay, well, we just evaluated what f of x plus h would be. Okay, f of x plus h is this negative 7x minus 7h. So I'm going to plug that in place of this. So this is going to become negative 7x minus 7h. Now, we know what f of x is, right? F of x is negative 7x. So that is going to come here and replace this f of x. So this will be minus negative 7x, and all of that over h. And now we just want to simplify this, okay? So something should cancel out at this point. In my numerator, I've got negative 7x minus negative 7x. That's the same as negative 7x plus 7x, right? So these actually end up canceling out. And all I'm left with is negative 7h over h. Right, so negative 7h over h. And now at this point, since I just have multiplication and division left, the h's will cancel out, and I just get negative 7. Okay? So to evaluate a difference quotient here, we need two things, right? First, we need to evaluate f of x plus h, meaning I'm plugging x plus h into my original function wherever I see an x and simplifying that, and then taking the difference quotient here, plugging that in for f of x plus h, and then taking f of x down here and canceling whatever I can. Okay? Let's do another example here. Okay, let's do this one together. So again, I want to first evaluate f of x plus h. Okay, so f of x plus h. So I'm plugging x plus h in place of x. So this is going to become x plus h squared minus 5. Now I want to simplify this, okay? Which means I'm going to have to expand out this x plus h squared. Now remember, whenever I'm squaring a binomial, I cannot just square each term individually, right? We have to either think about this as x plus h times x plus h, or if you know the shortcut, right? The shortcut is square the first, take 2 times the product of the 2, right? So that would be x times h times 2, or 2x h, and then square the last. All right, and then minus that 5. Now, if you don't know the shortcut, that's perfectly fine, right? You can come off to the side here and do x plus h times x plus h, right, and FOIL this out. That's perfectly fine. Okay, but the shortcut, whenever you're squaring a binomial, is square the first, take 2 times the product of the 2, and then square the last. Okay, so now let's evaluate our difference quotient. And when we do this, I like to use parentheses, right? So the first thing is f of x plus h minus f of x all over h. So f of x plus h is this whole thing, x squared plus 2xh plus h squared minus 5. That's my f of x plus h, right? Then minus f of x, so minus x squared minus 5. Use parentheses so that you keep all of your negatives and subtraction signs straight, and that's all over h. So now at this stage, some things should cancel out. All right, I've got x squared minus x squared, so those will cancel. And then I've got negative 5 minus negative 5, so those will cancel. And I'm left with 2xh plus h squared all over h. Okay? Now, if we look in the numerator, I can factor an h out of the numerator, and I would be left with 2x plus h, right? And that's still all over h. Now, I can cancel out these h's because they're being multiplied. And all I'm left with then is 2x plus h. Okay? So again, evaluate f of x plus h, and then plug that into the difference quotient, which is f of x plus h minus f of x over h. Some things should cancel out. And then at the end, we should eventually be able to get rid of that h in the denominator. Okay, but we have to be careful with our canceling. Remember, we can only cancel things that are being multiplied. So I want you guys to take a couple of minutes here and try this last one. All right, let's take a look. So first, we need to evaluate f of x plus h. So I'm plugging x plus h in everywhere I see an x. So this will be x plus h squared minus x plus h. So there's a lot of expanding to do here. Remember, 2 times the product of the, or I'm sorry, square the first, plus 2 times the product of the two, square the last. Then I can distribute this negative sign in here and say this is just minus x minus h. I don't think there is anything I can combine there, right? So I've got a large expression for f of x plus h. Then I'm going to plug this into my difference quotient. My difference quotient is f of x plus h minus f of x all over h. So my f of x plus h is this whole long thing, x squared plus 2xh plus h squared minus x minus h minus my f of x, and my f of x is x squared minus x. So I end up getting a couple of things to cancel out. I've got x squared minus x squared, so those cancel. And then I've got negative x minus negative x. So that would be the same as negative x plus x, so those cancel. And that's still all over h. So what I'm left with is 2xh plus h squared minus h all over h. And now I can take an h out of every term in the numerator. And be careful here. What we're left with then is 2x plus h minus 1. Right? If I take an h out of that last term, it doesn't just go away. Remember, that's the same as dividing everything by h if I factor an h out. Right? So if I factor an h out of h, I'm left with a 1. And that's all over h. So now I can cancel out these h's, and I'm left with 2x plus h minus 1. All right? So the homework we'll work on tomorrow in class, but if you want to get a head start on it, you are more than welcome to.